Hi, my name's Andrew, and in this talk I'll give a very short overview of our project on sound invariant generation for continuous and hybrid systems that we are pursuing at Carnegie Mellon University together with my co-authors, Nathan Fulton, Stefan Mitsch, Andre Platzer, who is our principal investigator, and Jon Kempton. So the broad context of our work is a theorem prover called Chimera X, which implements a differential dynamic logic, or DL. This logic, for example, allows one to specify and verify properties of hybrid systems, such as safety properties. The prover is guided through a web interface and is available for all to download from www.chimerax.org. The user builds formal proofs in Chimera X in a bottom-up way, using rules provided by the system, which may result in sub-goals. One of the big problems with this approach is that formal verification is often a very tedious process, and in particular for constructing safety proofs, one often requires invariants with which to reason about safety. And because we're dealing with cyber-physical systems, we often rely on finding appropriate continuous invariants, and this often requires an insight into the physics or the workings of the system at hand. To be a bit more precise, a continuous mode in a hybrid system is often given in terms of an ODE, or an ordinary differential equation, such as this one. So here, primes denote the time derivative, and the right-hand sides are given by continuous functions, which in our case are polynomial. To write this down more concisely, we can use vector notation. And a continuous invariant I is simply a formula that satisfies this property, which says that essentially I is preserved along the flow of an ODE. Proving invariance properties such as this one has improved tremendously in DL, owing to the work this year by Platzer and Tam, which essentially takes care of checking this part of the premise. However, there is still the problem of finding appropriate invariance I, such that a safety proof such as this one can actually go through. So for this purpose, we've developed a dedicated invariant generator that we've called Pegasus, which receives a continuous safety assertion from the Chimera X prover and then attempts to generate an appropriate continuous invariant that it then hands back. So it's important to note that in this architecture we do not compromise any soundness, because even if Pegasus gets something wrong, the invariance property still needs to be established in the sound DL calculus. So the system really works by first classifying a problem that it receives from Chimera X, and then based on a number of discriminating criteria, such as the dimension or the type of nonlinearity, it calls one of its implemented invariant generation methods, which may also be organized into invariant generation strategies. Now, a big part of Pegasus is based around this notion of discrete or qualitative abstraction of a continuous system. Shown here on the left, for example, is a continuous system, a vector field of a continuous system where these arrows follow the trajectories. A discretization is performed using a number of functions whose sign conditions can be used to partition the continuous state space into a number of discrete entities, and we can then study the transition relation between these discrete states to arrive at a more simple discrete abstraction shown here on the right. Now, in order to perform this abstraction, we built it on our earlier work that we published in 2016 and extended with other methods that we've developed lately. So the biggest part of the discrete abstraction algorithm is coming up with polynomials with which to perform the discretization, and a particularly useful class of polynomials for this purpose are Darboux polynomials. Now, polynomial is Darboux if its derivative is given in terms of the polynomial itself times some cofactor. If this is true, then the set of zeros of such a polynomial is itself invariant. And this is all the more interesting because people have studied ways of generating Darboux polynomials in fields such as computer algebra, and we implement some of these algorithms. For example, in a system shown below, we have a system with 4 Darboux polynomials which partition the state space of the system into disjoint regions between which there are no transitions whatsoever. So a Darboux polynomial can in essence be used to shatter the continuous state space of a system into completely disconnected entities, and this enables us to study the discrete states separately. Now, another very useful class of functions we can employ for this purpose are known as first integrals or conserved quantities, and these are simply functions whose derivative is everywhere 0. As an example of an invariant that we can generate using Pegasus by employing first integrals, here is a system where the red regions represent the unsafe states, the 2 green regions represent the initial states, and the invariant generated using a first integral is represented by the blue regions. Now, an alternative to methods based on discrete abstraction is a method of barrier certificates, which was originally due to Prajna and Jadbabaye in 2004. And the idea here is to find a real value differentiable function that evaluates to a strictly positive value in all the unsafe states, and then remains bounded above by 0 for all future time from all the initial conditions that emanate from our initial states. So, for example, if one is given the following verification problem, if one manages to find a barrier certificate which may look like this, one in essence obtains an invariant. So this shaded blue region is such that it separates the initial states from the unsafe states and cannot be left from within. So in our work we go further in that we generalize the entire method of barrier certificates, and we were inspired by the work done by Richard Bellman on vector Lyapunov functions in the 1960s. So in our approach we don't seek a scalar real valued function as before, but instead we seek a vector function b from Rn to Rm, such that for some element of this vector function it needs to remain strictly positive on all the unsafe states, and all of the functions in this vector need to remain bounded above by 0 for all future time as the system evolves from the initial states. So to give an example of what this looks like, here is a simple linear vector barrier certificate given by x1 and x2, which again separates the initial states from the unsafe states, but where the invariant region is given by this conjunction, which is obviously a much more expressive class of sets than was considered previously. So this work appeared this year at FM 2018. And unlike previous notions of barrier certificates that relied on a scalar differential inequality, in our work we employ a vector differential equality like this one, where A stands for a Metzler or an essentially non-negative matrix, which simply means that all the off-diagonal entries in this matrix are non-negative. And these matrices may be time-dependent if we wish them to be. So this in particular allows us to employ the vector comparison principle to search for conjunctive invariants, and generalizes previous notions of barrier certificates. So at the moment Pegasus is implemented in Wolfram's mathematical language because we rely on some very efficient computer algebra functionality in Mathematica. It is already integrated with the Chimera X prover, and this year in the Arch verification competition, Chimera X has been very successful in proving the vast majority of the nonlinear benchmarks, owing to the fact that it was able to make very effective use of invariants generated by Pegasus, which is a very encouraging development. So we also observe that the use of vector barrier certificates and barrier certificate-based methods generally is very promising, largely because we can generate them using tractable methods from nonlinear optimization. I should say convex optimization, such as methods employing sums of squares programming, and more recently linear programming relaxations such as Handel-1 representations. And there are certainly many more interesting methods that we need to explore. So our final goal in this project is to enable an automatic formal verification of control software for systems such as quadrotors. And properties of interest to us include things like ground avoidance and collision avoidance. So to wrap up, here is a list of references where our work is described in a bit more detail for those interested. And this brings me to the concluding slides. I'd like to thank you all very much.